Hi, we are about to talk about the last in our four-part series on the life cycle of stars. We'll be talking about how stars die, what happens when they die, and what happens after they die. This comes from OpenStax Astronomy, parts of chapters 23 and 24. As you recall, last time we were together, we had two different sets of stars. We had regular mass stars that were similar in mass to our sun, maybe slightly larger. We also had supermassive stars. In both cases, they had finished fusing everything that was in their core at least once and had begun fusing elements in their outer layers, which caused them to swell and inflate and become red, either red giants or red supergiants, and then to begin fusing other elements inside their cores, other more massive things. So we're going to pick up with our low mass stars. Once they have finished fusing everything that will fuse in their core, after they have already had their big helium flash, they have been fusing carbon. In some cases, they've been fusing on up to oxygen. When they run out of their last bit of material, they will again begin to crunch inward. Now, at this point, they've already lost a good bit of their mass through at least one planetary nebula. But at this point, there's nothing left that's going to reignite and begin fusing and begin pushing back outwards. So those stars are going to start to collapse. What's left there is going to collapse inward on the core, and that's just going to cause it to become more dense, which is going to increase gravity and cause outer layers to collapse in even more so on it. Excuse me. And when that happens, all of those particles, all the atoms, are getting crunched together very, very tightly. Now, the electrons aren't going to want to go along with this. The electrons are going to repel each other. They're not going to want to try and share the same state. Pauli exclusion principle, you can't have two electrons, with the same set of quantum numbers. They can't fill the same space. And so they're going to provide some outward pressure that is going to cause that crunched down core of protons and neutrons to sort of stabilize. Once that happens, and once all fusion is completely and totally gone, the star is considered to be dead. But at that point, what's left over is called a white dwarf, and it's going to continue to give off light and energy for potentially billions of years, because it's not going to require fusion to keep on going. It's just going to be radiating out, what energy is left in there. Eventually, when it does completely and totally cool off, it will stop radiating light, and it will be what's called a black dwarf. But what's really cool, because so many of them at this point are basically solid carbon, as it cools off, those carbon atoms, which are pressed in very, very tightly, are going to arrange themselves in very regular crystals. And basically what you're going to have is a big floating diamond out in space where there used to be the heart of a star. And that sounds great, except one, there's none anywhere near enough to us to be able to get to them, and two, by the time you got to one, you would be crushed beyond recognition by its immense gravity. But I just thought, if you're going to go out and go out graciously, I think that's a pretty classy way, a pretty classy thing to leave behind. Well, you can see in this diagram right here, this is actually visible light of the Sirius Star. This is Sirius A, is the big star that's taking up most of the space right there, most of the brightness. This is in the Canis Majoris, or Big Dog constellation. You can see this little spot right down here to the left. That's actually a little white dwarf. That's Sirius B. Now, these two are in a binary star system, meaning that they orbit each other. In Sirius B, no telling how long it's been a white dwarf, and it just barely shows up on visible light. But when you shift over to X-ray, the bright spot you're seeing right there is actually Sirius B. It's actually the dead star. So it's continuing to give off light, not always visible light, but it does continue to radiate energy for billions of years after the last big crash. Now let's take a shift over to look at those supergiants. Supergiants, remember, by the time they were nearing the end of their life, they had fused increasingly larger and larger elements until they had a core of iron. Iron is not going to give off energy when you try and fuse it, though. And so very quickly, this star is going to hit crisis point. Whenever its fusion stops, then the outer layers are going to begin collapsing in on it, very similar to what you saw in the lower mass stars. A big difference is that since there is so much mass, the gravity pulling it in is going to overcome those electrons that were kind of struggling against that, and it's basically going to suck them in to the nuclei of those atoms. And so those electrons are actually going to crash into the nuclei of those atoms. They're going to collide with protons, which is going to change the proton into a neutron, and then it's going to emit a particle called a neutrino. And so you've got this very, very dense heart of this star that is now basically a giant block of neutrons. Those electrons aren't there to resist further collapse, and so at the very last stages, the outer layers are going to collapse in close to a fourth of the speed of light. Very, very sudden crash. And when they do that, a lot of the neutrons that are left in there are going to start to escape at very high speeds. And so that center ball of neutrons is going to stay steady, the core, but the other neutrons and other particles rushing out from there, they rush out with so much violence that it basically explodes the rest of the outside of the star and throws it off in a huge cataclysm called a supernova. In fact, what we're talking about right here is what's called a type 2 supernova, and we'll discuss why that's type 2 in just a few minutes. But one of the questions from the last video is asking, well, if a star can't make elements bigger than iron, how do we have elements bigger than iron? And here's your answer. As those layers are being blown outward, and as those other neutrons and other particles are rushing out, and in some cases catching them or passing them, they smash into atoms of other elements, and they are absorbed. And so you start getting larger and larger elements. You start getting nickel, you start getting cobalt, and on until you get up to uranium, which is the largest naturally occurring element. And so a lot of those elements, especially our heavier elements, owe their existence to these violent supernovas, these violent explosions. And what you see in the picture right here, this is the remnant of the Kepler supernova, which erupted around 400 years ago, and it's still giving off energy. At this point, the remnant of that supernova is about 14 light years wide, and it's continuing to expand at around 4 million miles per hour, so there's still quite a bit of energy. Now, down in the heart of that guy, and in fact, that ball of neutrons that survived that explosion, it becomes what's called a neutron star. And neutron stars are the densest objects in our universe. And I can say that because, technically it's still up in the air as to whether black holes are in our universe or not, but we'll talk about those in a minute. And so these neutron stars, you've got the mass crunched down into something that's about the size of a small town. And so if you imagine like the town of Borger, the town of Stinnett, only that small of a space is exerting about 10 to the 11th the surface gravity of Earth. And so you're having about, 10 billion times the gravity of what we're experiencing right now. It's absolutely immense. One of the ways that we know that these things exist is around the 1960s, some researchers started noticing that certain areas of space seem to be shooting them regularly timed radio signals. And first of all, the buzz was, well, apparently the aliens are finally contacting us. But what was happening is that a lot of these neutron stars, upon their formation, they are set to spin. And as they spin, they are radiating out these hot jets of particles. And it's kind of like the beam of a lighthouse passing you by and then doing it again at a regular interval, except the interval here was, every 1 or 2 seconds. And they nicknamed those things pulsars before they knew what they were, and then when they looked a little bit closer, they found, oh, well, that's in the middle of a supernova remnant, and this must be what's kicking this off. Now, that's one avenue that these supermassive stars can go down. If a star is anywhere from 10 to 40 times the size of our sun before it begins all of its life, it will end up typically as a neutron star. If you've got stars that are even bigger than that, they continue contracting even past the neutron star phase. There is so much matter and so much gravity that literally these things completely and totally collapse in on themselves, and they rupture little holes in space-time. At the areas where this happens, space and time, their flows will slow down and even theoretically stop. What we're referring to have come to be known as black holes. And so that happens when you've got a type 1 supernova. The reason why this is type 1 and the other is type 2 is for the longest time, theoretically, this is the only possible scenario that theorists had worked out as being the final stage of these supermassive stars before pulsars and before neutron stars were discovered. Now, in a nutshell, a black hole is not a big whirlpool in space. It's not like you may have seen in movies. It is a place where space and time slow down and cease to exist. It consists of 2 parts. It consists of a singularity, which is a point at the heart where you have infinitely high mass and infinitely small volume. And then outside that, there's an area called the event horizon. And the event horizon is kind of the point of no return. If I get close to the event horizon, then the gravity is going to begin affecting me. But once I cross the threshold of that event horizon, then there's no escaping the gravitational pull of that black hole. Whether I am light, whether I am matter, whether I'm energy, radio waves, whatever, nothing gets back out. What we see in this bottom picture here, this is the first close-up photo taken of a black hole. This is black hole Sagittarius A that was developed back in 2019. Up at the top you see kind of a NASA artistic interpretation of what might actually be seen if we could get a little bit sharper picture. And what you're noticing here is that there is so much distortion on space-time that it acts kind of like a lens, and it literally bends light and refocuses light around it. There's a written account that is from the chapter. I'm going to read to you more or less in its entirety, and I'm sorry if this put you to sleep, but I just thought that the account here was so really incredible. So feel free to fast forward if you would rather not hear me read. The fact that scientists cannot see inside black holes has not kept them from trying to calculate what they are like. One of the first things these calculations showed was that the formation of a black hole obliterates nearly all information about the star that collapsed to form it. Physicists like to say that black holes have no hair, meaning that nothing sticks out of a black hole to give us clues about what kind of star produced it or what material has fallen inside. The only information a black hole can reveal about itself is its mass, its spin, and whether it has any electrical charge. What happens to the collapsing star core that made the black hole? Our best calculations predict that the material will continue to collapse under its own weight, forming an infinitely squozen point. I love that word, squozen. A place of zero volume and infinite density, to which we give the name singularity. At the singularity, space-time ceases to exist. The laws of physics as we know them break down. We do not yet have the physical understanding or the mathematical tools to describe the singularity itself, or even if singularities actually occur. From the outside, however, the entire structure of a basic black hole, one that's not rotating, can be described as a singularity surrounded by an event horizon. Compared to humans, black holes are very simple. They've only got two parts, as far as we can tell. Scientists have also calculated what would happen if an astronaut were to fall into a black hole. Let's take up an observing position a long, safe distance away from the event horizon and watch this astronaut fall toward it. At first he falls away from us, moving ever faster, just as though he were approaching any massive star. He's being accelerated by gravity. However, as he nears the event horizon of the black hole, things change. The strong gravitational field around the black hole will make his clocks run more slowly when seen from our outside perspective. If, as he approaches the event horizon, he sends out a signal once per second according to his clock, we will see the spacing between his signals grow longer and longer until it becomes infinitely long when he reaches the event horizon. As the spacing between clock ticks approaches infinity, it will appear to us that the astronaut is slowly coming to a stop, frozen in time at the event horizon. In the same way, all matter falling into a black hole will also appear to an outside observer to stop at the event horizon, frozen in place and taking an infinite time to fall through it. But don't think that matter falling into a black hole will therefore be easily visible at the event horizon. The tremendous redshift, the tremendous delay in the light we're getting makes it very difficult to observe any radiation from the frozen victims of the black hole, which is why that one picture from 2019 was so groundbreaking. This, however, is only how we, located far away from the black hole, see things. To the astronaut, his time goes at its normal rate, and he falls right on through the event horizon into the black hole. Okay, the event horizon is not a physical barrier, so there's nothing literally stopping him. It just keeps anything from escaping. You might have trouble with the idea that you, watching from far away, and the astronaut falling in have such different ideas about what's happened. This is the reason that Einstein's ideas about space and time are called theories of relativity. What each observer measures about the world depends on its relative to his or her frame of reference. The observer in strong gravity, the astronaut, measures time and space differently from the one sitting in weaker gravity, that would be us. When Einstein proposed these ideas, many scientists also had difficulty with the idea that two such different views of the same event could be correct, each in its own quote-unquote world. And they tried to find a mistake in his calculations. There were no mistakes, though. We and the astronaut really would see him fall into the black hole very differently. For the astronaut, there is no turning back. Once inside the event horizon, the astronaut, along with any signals from his radio transmitter, will remain hidden forever from the universe outside. He will, however, not have a long time from his perspective to feel sorry for himself as he approaches the black hole, whereas for us it appears he's taking an infinite amount of time to fall in. For him, it's going to seem like time is functioning as normal. Suppose he's falling feet first. The force of gravity that the singularity exerts on his feet is greater than on his head, so he will be stretched slightly. Because the singularity is a point, the left side of his body will be pulled slightly toward the right and the right slightly toward the left, bringing each side closer to the singularity. The astronaut will therefore be slightly squeezed in one direction and stretched in the other. Some scientists like to call this process of stretching and narrowing spaghettification. Love that. The point at which the astronaut becomes so stretched that he perishes depends on the size of the black hole. For black holes with masses billions of times the mass of the Sun, such as those found at the centers of galaxies, the spaghettification becomes significant only after the astronaut passes through the event horizon, because it is so much larger. For black holes with masses of a few solar masses, the astronaut will be stretched and ripped apart even before he reaches the event horizon. Something similar happens to spacewalkers around the Earth. In the case of Earth, the forces are so small that they pose no threat to the health and safety of the astronauts. Not so in the case of the black hole. Sooner or later, as the astronaut approaches the black hole, the tidal forces will become so great that the astronaut will be ripped apart, eventually reduced to a collection of individual atoms. They will continue their inexorable fall into the singularity forever. That's a happy thought to end on. And so this very last slide is just kind of for your reference. Up at the top we've got a table showing, based on the initial mass of a star when it first starts burning on the main sequence, and its predicted end-of-life state, all the way from things that never tend to be stars that end up as planets or brown dwarfs, all the way up to those type 1 supernovas that leave black holes. We also have the standard diagram here tracing life cycle of stars on their two main branches from birth in a stellar nebula all the way up to the different deaths that we discovered here. Not much difference between that and what you probably saw in 8th grade. And this last one right here is just because anytime you try and Google for images of the death of a star, it's funny how often this guy keeps popping up. Anyway, I hope you have enjoyed our discussion on the death of a star and what happens after, and thanks for watching.